What is up, amigos? Today we're looking at flow separation. We're looking at what it is, why it happens, and consequences. So flow separation can happen over really any object. We can have a regular circle, we can have an airfoil, we can have some weird shape, and the flow coming in will often separate over these objects here. So what is it? So for example, the circle here, if the flow comes in and then it goes over the top, they'll get a point where the flow will then lift off and it won't really follow this geometry anymore. That is flow separation. Then what happens is we have additional flow behind here, which is just general chaotic motion. And depending on the object, it can be quite predictable. In other cases, not very predictable. So for this airfoil, for example, the flow will come over and then it might again just detach. And then we get some sort of wake happening here. And for this object again, it might just detach. So we get some wake. So why does it happen? Well, there are a couple of different reasons. And for these two top geometries, we're looking at something called the adverse pressure gradient. So if we just have a regular curved surface, so this can approximate the airfoil or a really big circle, the flow comes through, and as it goes over this surface, it starts to accelerate. We know that the flow over a curved surface starts to accelerate. So the pressure drops. But then once we get to a certain point, there's actually this back pressure acting on it. So the further along this flow goes, the higher the pressure gets. This is called an adverse pressure gradient. So we say the change in pressure as we go along the x direction is positive. So it's pushing back and it's getting more and more. And it gets to a point where the flow very close to the wall becomes so decelerated that it's actually moving backwards, and then it will start to lift off. And that's when we get this flow separation occurring. The other point where we get flow separation is when we have quite sharp edges. And this is where we look at something called the radius of curvature. So if we have a very sharp edge like this and the flow comes along, trying to stay attached over that peak there is very difficult to do. You need a lot of energy. So naturally it would then just detach. So that's because the radius of curvature is very small. We want to have a very large radius of curvature, very sweeping, and then that will allow the flow to stay attached more. So if we curved it more like that, the start and end points are the same, but this middle section is curved, and that will allow the flow to stay attached much more easily. So that's why it happens, and the consequences are that we get a very large wake, which usually results in the pressure drag increasing a lot. And if you don't know what the pressure drag is, check out this video here. And in addition to that, the wake becomes quite, as I mentioned, quite chaotic, but also unpredictable at times. So in this particular case, for the circle, we get this periodic shedding from one side to the other, and that results in this fluctuation in pressure on this surface, and then it results in a side force as well, which then can rock this geometry and even break it at times. So that is flow separation. If you like this video, make sure to like it and subscribe. And if you see more like this, check out our other videos. And if you want to learn more about this phenomenon, check out a book by John D. Anderson in the link in the description. I'll see you next video. Peace out, amigos.